In this video, I'm going to talk about how to create an effect like this using curl noise. This is the network, and we're going to recreate this from scratch. But before we do that, I'd like to talk a bit about curl noise. And I'm going to borrow some slides from a presentation by Peter Werner, where he describes curl as a mathematical operation, just like plus or minus. And its input is a vector field and its output is another vector field. It measures the rotation at any given point on the field. And in the case of curl noise, the vector field is generated by a Perlin noise. So here's an example of that, and here is the curl of the same field. If we take these vectors and use them as velocities of particles in a particle system, the resulting movement is something like a fluid. It has a turbulence, it has some vortices, it's generally quite cool to look at. And it is also a lot less expensive to compute than classic fluid simulation. And easier to control as well, because we can tweak the parameters just like we tweak the parameters of any other noise. If you want to know more about curl noise and how it is calculated, I definitely recommend Peter's presentation. So I'm going to leave a link in the description. So here's our network. Let's get rid of everything and start from an empty file. The first thing we want is a box SOP. And we want it to be a bit shorter, so size Y is going to be 0.5 and also a bit deeper, so size Z is going to be 6 and the overall scale 0.1. From the box we can drop a null, and from that we can start with our standard rendering setup. So middle click and then pick a geometry comp, and then we also need a camera comp and a light. Next we need a render top, and from the render we can drop an alt top and toggle the display flag. Then we can add some background to our scene, so let's insert an operator here and pick an over top, and for the second input we want a ramp. Need to remember to switch this to input 1. And for the ramp we want the type to be circular and extend left to be hold. For the first color here on the left hand side, I want it to be a dark gray, so something around 0.2. And for the other color on the right, just drag it all the way down to 0 to get a black color. Last thing is a material. Pick a Phong mat and just drag it on top of Geo and select parameter material. This is it in terms of geometries and rendering. And now we need an operator to drive the animation on these boxes. And I'm going to use a GLSL top with the compute shaders. If you're not very familiar with compute shaders, I have another video about it, which I did in preparation for this one. So if you have any questions, please go and refer to that video. Here we're just going to go ahead and drop a GLSL top. Under mode we want to switch to compute shader, and for the version we want 4.30. Now we can hide our pixel shader and reveal the compute shader. And then we can click on edit to launch an external text editor. And we can get rid of these comments. Now when working with compute shaders, it's important to decide on the output size. And we're going to use this size many times, so it's a good idea to store it in a constant. So we're going to drop a constant chop. And I'm going to call this size and set the value to 64. And then we go to the command tab of our GLSL top and drag the size to resolution X and copy the expression and paste it for resolution Y. Now we can also use the same size constant to define our dispatch size. We already know that our local size is 8 by 8, so we can paste our same expression here and divide it by 8. And again, the same for both x and y. And then we need 3 operators to use as inputs connected to our GLSL top. One for position, one for velocity, and one for the initial state of our particles. So let's start with the first one, which is going to be a select top. The second one is going to be a constant top. And the third is going to be a noise top. Now we just need to connect them to the input slots. So let's change the constant to black, so 0, 0, 0. And we also need to change the size of all of these tops and use our size constant. So if you still have that expression copied to your clipboard, just paste it for both x and y, and do the same for all of the 3 tops. The third input, this noise top here, is going to be the initial position of our particles. So I'm going to call this top ini buffer. And the first input, which is going to be our positions, is going to select from the initial positions. So I want the target top here to be also ini buffer. Now we can go back to our shader and read the colors from these inputs. Let's get rid of these lines and repurpose this one. Instead of color, I want a vec4 p for position. And I'm going to duplicate this line and call it v, and it pointed to the input index 1, and then duplicate the line again, call it I, and point it to input index 2. These are storing all 4 channels from the inputs, but I also want some other convenience variables storing only the RGB channels. So I'm going to type vec3 pos equals p.rgb, then duplicate that, vec3 vel equals v.rgb, and one more, vec3 ini equals i.rgb. And now our compute shader is going to output to 2 color buffers, one for position and one for velocity. So we can bring this line up here, and instead of color we want to write a vec4 of pos, and for now a constant of 1. And we can duplicate this line and change the output index to 1, and the color is going to be a vec4 of vel and also a constant of 1. And we get an error message because our number of color buffers is only 1, so let's change that to 2. And we can see our first buffer in the viewer of the GLSL top, but in order to see both buffers we need to render select. So let's drop a render select and set the target to GLSL 1, and let's change the color buffer index to 0. And then copy the render select and paste it again, and change the color buffer index to 1. Now we can see both of the outputs of our shader. The first one, I want to rename it to pos buffer, and the second one to vel buffer. We're not really doing anything with our shader yet, but we can already use pos buffer to drive the instances in our geometry comp. Switch instancing on, and for our translate top we want pos buffer R, G, and B. Let's zoom out a bit. So in our camera, let's change translate Z to 15. And it doesn't look very interesting yet. We're essentially just taking our ini buffer, selecting it, passing it through our shader, and using it again as pos buffer. So let's edit our ini buffer. Go to the noise tab and switch off monochrome. The result is this kind of blocky cube, which is also a bit offset to the top and to the right. So let's correct that. Let's change the amplitude to 1 and the offset to 0. Now it looks like we lost 3/4 of our cube, and that is because of the pixel format. So we want to change from 8-bit fixed to 32-bit float. And then we get a more interesting kind of organic shape with the boxes clustered around the center. Now we need to finally do something with our shader, and what we want to do is to change the position based on the velocity and change the velocity based on curl noise. For the position, this is as straightforward as typing pos plus equals vel. And for the velocity, it's very similar. We're going to type vel plus equals noise. And in order to calculate noise, we need a curl noise function. We're not going to go through the implementation here because luckily for us, some smart people have already implemented it and made it available online. I'm going to use GLSL curl noise by Kabibo. Now all we have to do is to copy these lines and paste them in our shader. You might have noticed that his code is requiring a function called sNoise from GLSL noise, and that is to calculate the simplex noise 3D. Again, luckily for us, TouchDesigner already provides us with that. And we can find that if we go to our GLSL top and click on help. And then click on write a GLSL top. And under built-in functions, click on Perlin and simplex noise. Here's our simplex 3D. We just need to copy that and replace all 3 occurrences of sNoise. Now we're ready to use our curl noise function. So let's create a vec3 noise, and that will be equal curl noise, and we can pass our pos vector. Save that, and now we can see that our velocity buffer has some data, but it's all static, and in order to make it move we need to pass some time to our shader. So let's create a uniform u time, and let's use the classic abstime.seconds. Now we can declare that uniform here, so uniform float u time, and then inside our curl noise function we just add u time to our position. Now we can see that the data is changing, but our boxes are still static, and that is because we're only writing to these output and we're not reading from them. And the way to do that is with the feedback top. So let's drag this over here and insert a feedback top. And we want the target top to be pos buffer. Now I'll do the same for the constant. Drag it over here, insert another feedback top. And the target is going to be vel buffer. Now as soon as we do that, we can see that the boxes explode and go out of view very quickly. And that is because the values are still too big. So we need a few knobs that we can turn in order to control these values. So we can pass a few more uniforms to our shader. The first one I want is the step, or the elapsed time between each frame. I'm going to call that u delta, and it's going to be abstime dot step second. And the second one is going to be a vec4. Instead of creating 4 different uniforms, I'm just going to create a single one, and I'm going to call that u noise vector. And the values can be 0.5, 0.2, 0.2, and 0.2 again. Now let's declare those uniforms. So uniform float u delta and uniform vec4 u noise vector. And now we can use those to control our vec3 noise. So let's first use u delta, and then multiply that by noise factor x, and then we can multiply the position inside the function by noise factor y, and the time by noise factor z. And we can also use the last component down here and multiply this by noise factor w. Now we just need to reset our position feedback and also reset our velocity feedback. And we can see that the motion now is a lot more controlled. But still the boxes go out of view, and that is because the velocities keep growing. So we need to pass another uniform, which I'm going to call u-vel damping, and the value is going to be 0.96. Now let's declare that uniform. And after we add our noise, let's just type vel times equals u-vel damping. Now let's reset our feedbacks again, and we can see that the motion is much better. But still, given enough time, the boxes would eventually be outside of the viewport. It would be nice if we could reset them to the beginning. And we have some spare capacity in our position buffer because the alpha channel is not being used, and we can use that for a live parameter. So in our shader, let's type float live equals to p.a, and on every frame we're going to subtract from live a very small amount, like 0.005. In fact, this could also be another uniform. So let me cut this and go back to our GLSL top and create a new uniform called u-live damping, and then I can paste 0.005. Now we declare our u-live damping and just subtract that here. And then we need to check if live ever goes below that value. So if live lesser than or equals to u-live damping, we want to reset live back to 1, and we want to reset the position back to the initial position. Now we need to use live as the alpha channel of our output. Let's reset the position feedback once again to see the result. And the boxes are getting reset, but they're all getting reset at the same time. And that's because they're all born at the same time. If we look at our initial buffer, we can see that the alpha channel is a constant of 1. So let's change that. Let's go to the output tab, and where it says alpha 1, let's change that to alpha input. And then we want to drop another noise stop to use as input. And we have to remember to use our size constant. So let's drag that here for resolution X and resolution Y. Now in the output tab, let's change alpha to noise. And in the noise tab, let's change the type to random. Now we connect that to our ini buffer, and we can go to the output tab and select RGB noise. Now we can see that the alpha channel has varying numbers. And since we're using 32-bit float for everything, let's also change the pixel format of our input noise here to 32-bit float. Reset the position feedback once again, and we can see the result. Now the boxes are appearing and disappearing at different times. Next, we can make our boxes face their direction of travel, and TouchDesigner made this really easy for us. All that we have to do is to use another operator in our instance 2 tab, the rotate to OP. We want to use our vel buffer, and for XYZ we want again RGNB. And the effect is now a lot closer to what we're after, but there are still a few things that we can improve on. We can see that the boxes just disappear at the end of their lives, and we can maybe shrink them so that they're very small just before they disappear. And again, we still have some room in our buffers to do that, and that is the alpha channel of the velocity buffer, which is still not used. So let's use it. Let's create a new variable, float size, and it can be just equals to life. And then pass it in the alpha channel and go back to our geometry, and in the instance tab the scale OP is going to be vel buffer and scale Z is going to be A. We can see it's doing something, but there is a glitch, and that is because of the order of our transformations. So in the instance 2 tab, change the rotate order to pre-rot. And now it is kind of working like we wanted, but it would be nice if they could first appear small, then grow to full size, and then shrink again before they disappear. We would need a function that starts at 0, goes to 1, and then goes back to 0. And we can get exactly that in this article by Inigo Quiles called Useful Little Functions. The one we're after is the parabola. So all we need to do is to copy that and paste it into our shader. Then we can use that to calculate the size. So it's going to be parabola 1 minus life, and I'm going to use a factor of 1. Now it's already looking much better. The last thing we want is to add some color. So let's drop a ramp top. And for the first color, I want something like a dark green blue. And for the second color, I want something like a bright red. Let's go back to the geometry comp, and in the instance 2 tab, under color OP, let's pass ramp 2, and then R, G, and B. I forgot to use our size constant. So we need to drag it for both X and Y. Now it's looking a lot closer to what I showed you at the beginning, but it is a little bit sparkly. Let's go to our phone mat and change the specular to black, and let's bump the diffuse to full white. So it's looking good. Feel free to play with the noise factor, find some other values that you might like. Another thing we can do is to add a shadow pretty much for free. So just go to the light comp and select a shadow. And the last thing I want to do here is to change the number of boxes. At the moment we have 64 by 64, so that's about 4,000 of them. Let's change this to 256 and get about 65,000. And that's it. I hope you liked it. If you have any questions, feel free to ask. Otherwise, until the next video.